Third section in chapter 16. So chapter 16, we're talking all about electricity, and in this particular section, we are going to be talking about specifically resistance and Ohm's law. So resistance, we've talked about a little bit, but we're going to write the formal definition down now. So resistance, the measure of how strongly a wire or other object resist current flowing through it. So remember, we're imagining electricity like water flowing through pipes. So just like water flowing through pipes, it's going to meet resistance for various reasons. Think about, if you change the size of that pipe, if it's larger versus smaller. Think about how much water is going through there. Is that going to change, the resistance of that water going through the pipe? So electricity can be changed essentially in the same way. So if you look at the picture on the right-hand side there, we have two different sort of bottles, if you imagine them, and imagine one of them just has a tiny opening for that water to come through, so it's going to be a much higher resistance for that water coming through, whereas the one on the right-hand side there, much larger opening for the water to flow through, so there's less resistance as that water is coming through. So low resistance is going to be able to carry a large amount of current, as you can see the picture on the right. High resistance or items that have high resistance carry almost no current. It's not going to have that ability to push the electricity through. So you see on the bottom there, the picture with the light bulbs, they're showing you some simple circuits. So in the first one, we have just one light bulb, one battery, full current going. You can see lots of electricity going to that light bulb. It's really bright. Now look at what happened. We added another light bulb in there, same amount of power. I have the same battery there, 1.5 volts, and it's half the current that's now running through that circuit. So you're going to have twice the resistance because that electricity is having to go through each light bulb. So really, the light bulbs are going to start to light up less, if that makes sense. Finally, on the last one, now I've added even in more resistance, another light bulb. Remember, anytime we're adding something in a circuit, it's going to slow down that electricity. So if I'm adding it in, it's going to slow it down, and those light bulbs are not going to be as bright there. So every time we add a device, it's essentially adding resistance to that circuit, if you want to think of it that way. So units of resistance that we use is called the ohm. So those are what we measure resistance in. So you can see that sort of like weird Greek symbol that we have there. That is the Greek letter for omega. It's kind of easy. It almost looks like an upside down U a little bit when you go and write it, if you want to think of it that way. A couple of things, like looking at the picture on the right hand there, we can actually use one of those multimeters that we talked about earlier to measure the resistance in an object. So really all you got to do is take the two leads on the multimeter and you set it up on the device which you're trying to set the resistance to. You actually change the dial on the multimeter to that thing, and you can see that particular light bulb would have a resistance of 4.9 ohms. Just to give you another idea, the picture on the bottom there, 1 volt in a circuit creates a current of 1 amp, and then you're going to have a resistance of 1 ohm going through there. Just another thing here that I'm forgetting. So wires and electric circuits have low resistance, and that's because they're often made of elements like copper or aluminum. Those are elements that have a low resistance to them, which makes sense. That's why they're really good at conducting electricity. And usually we kind of ignore whatever resistance is going through them. Obviously there's going to be something, but it's negligible enough that we don't account for those in a circuit when we are making those calculations. Probably one of the most important laws in electricity, anytime we're dealing with electricity, is Ohm's law. So Ohm's law simply states that current is directly related to the voltage. So when we say directly related, you got to remember what that means. So if one thing goes up, the other thing is going to go up. So if we double the voltage in a circuit, it is going to double the current. Think of that. You're doubling the voltage, you're doubling the push. So if you're increasing the push, it's going to increase the amount of current that's going through there. More push, more current. What it also does is it has an inverse relationship for resistance in the circuit. So if I double the resistance, so think of that, I'm doubling the resistance. So imagine now taking that wire and you're making it smaller and smaller and smaller because you're not letting that electricity go through such a large wire. What's going to happen to the current? If you were making that smaller, your current's going to go down. So if I increase resistance, current is going to go down. And that's all Ohm's law states. So it's actually a little bit of common sense there. There's the formula there. Current is equal to voltage divided by resistance. Current is measured in amps, but in Ohm's law formula, we use the letter I for the abbreviation there. You can see that on the bottom there. So it also shows you on the left-hand side there the three different ways we can move those variables around to try to solve for the other things. So that's Ohm's law. Current is equal to voltage divided by resistance. And just remembering, if I increase voltage, I'm going to increase current. If I increase voltage, increase current. If I'm going to increase resistance, I'm going to decrease current, which really completely and totally makes sense. It's kind of confusing when you first look at it, but it really is sort of common sense stuff. So just like any of the other problems that we've done in Science 9, you just take your formula, you plug things in. Here's an example problem. A toaster oven has a resistance of 12 ohms and is plugged into a 120 volt outlet. How much current does it draw? So current, voltage divided by resistance. So I just take 120 volts divided by 12 ohms, and then current, remember, is measured in amps. So the answer would be 10 amps. All right, so resistance of common objects your book talks about. So objects can vary in resistance anywhere from 1,000th of an ohm, which is obviously a really small resistance, all the way up to 1,000,000 ohms for resistance, which should be really big. So they can vary greatly. Because of resistance, all electrical devices will actually draw the right amount of power only when connected to the voltage that they're designed for. So for example, your book talks about a 100 watt light bulb, which we should be very familiar with, has a resistance of actually around 144 ohms. When you connect it to our electricity in our house, which is at 120 volts, which that's any wall socket, the current is 0.83 amps and the bulb lights. If you were to connect that exact same light bulb to a 1.5 volt battery, is it going to light? I mean, think about that. That same light bulb, you hook it up to a small battery like a AA, is it going to light? And most of us know that anyways, know it's not going to happen, but Ohm's law actually explains to us why that is. The current is only going to be 0.01 amps when you attach it to that 1.5 volt battery with the resistance of 144 ohms. So there's no way it's going to light the light bulb. So all electrical devices draw the right amount of power only when connected to the voltage that they were designed for. So you have to connect it to the right voltage, otherwise you're not going to get enough current to make whatever that electrical device is light up. The picture on the right there, the book just talks a little bit about if a device's resistance changes due to temperature. Some do, not all do. They're actually called non-ohmic, and that's because Ohm's law does not apply to those particular devices. Just wanted to show you that does happen. This section also goes into great detail about what conductors and insulators are. So conductors are materials that have low resistance. So those are things that we use to conduct electricity. So things like copper, aluminum, gold, and we all know those things as things that we have in anything that's going to conduct electricity. You can see in the chart on the right-hand side there, conductors, and I didn't even list all of them, iron, silver as well. So those things you're going to often find in electrical circuits. We find them in electrical wires that we are going to conduct electricity in. Insulators, these are things that do not conduct electricity well, and that is because they have a high resistance. So these are things like wood, rubber, air, glass. All of these things are what we call insulators. They have high resistance, electricity is not going to go through them. And it is great that we have these different properties for these different substances. When you take a look like at the wire there, it's great that we have a device that can conduct electricity, and then we can surround it with something that doesn't conduct electricity so that we do not electrocute ourselves when we are using things. Items that fall in between these two categories we call semiconductors, materials between a conductor and insulator in terms of carrying a current. This is great because some things in our circuitry, we want to have the ability to conduct electricity at times and not at others, and we call these things semiconductors. So these are things like carbon, germanium, The element silicon. Silicon should sound familiar to you because of Silicon Valley in California, which is named after, that place is named after large advancements that were made in technology with the help of the semiconductor silicon. Obviously, tons of technological companies out in Silicon Valley. Now you can kind of see why that is. Finally, last thing the section talks about more specifically are these things called resistors. So what you guys see on the bottom there, on the bottom picture there, there's kind of weird like color schematic things. Those are resistors. Now resistors, first of all, we have two different types. We have fixed resistors and then we have variable resistors. What you see on the bottom there, those things are fixed resistors. Because they're so small in a circuit, instead of labeling them with 10, whatever the actual ohms are, they use a color coding system, as you can see there, to measure and let someone know what the actual resistance of those particular fixed resistors are. It's kind of a cool little system you can see there, the one on the bottom with the red, the green, the yellow, and the gray. When you add all of those things up using the little chart on the side there would actually equal 25,000 ohms, which is pretty cool. On the right-hand side there, that potentiometer, you can see that is a variable resistor. So a variable resistor can actually be adjusted to give resistance within a certain range. If you have ever used a dimmer switch before in your life, you have used one of those. So the dimmer switch is on a light where it gets bright and then light, you're actually changing the resistance of the circuit, and that is how you are getting the different lights, is by just changing the resistance of the circuit using that small device that is found in there.